Alright guys, this is the forces and acceleration homework that I'm having you guys do for practice. You're going to take it as a quiz, but I thought I'd kind of go through some of the questions and kind of show you how to do some of them. You first off need to know your equations that you're going to be using for this chapter. Your force net equation is always the sum of force 1 and force 2, but remember, if force 1 and force 2 are going the opposite direction of each other, this would be adding a negative, right? So you could almost just change that out to a minus. So an example of that would be like if force 1 was force applied this way and force 2 is going to the left, then this plus up here would actually be a minus because these are going the opposite way. And opposite ways in mathematics, opposite means to do the opposite sign, right? And that's why we said at the beginning of the year, to the right and up is going to be positive, to the left or down is going to be negative. Okay, so I'm going to get rid of some of that stuff. Just to get that out the way. Excellent. Okay, so I'm going to show you number 3 first because number 3 is kind of a doozy. It's kind of challenging, and it also helps you with number 6. So let's go ahead and take a look at that real quick. A 9.2 kilogram bucket of water raised from a well by a rope. That means the net force is going upward, right? The acceleration due to gravity is 9.8. If the upward acceleration of the bucket is 3.5 meters per second, find the force exerted by the rope on the bucket. Okay, so this one, it's not quite as simple as you think. This is kind of a challenging, this is what I call an elevator problem. Alright, so we need to draw a free body diagram to kind of represent all the forces. We know that this is force gravitational, this is force tension, right, because that one's going upward. Okay, but now they give us some information here. We know there's a net force acting on the entire system because we have upward acceleration. Alright, so let's go ahead and look at our givens. I have acceleration of 3.5 meters per second squared. So you want to write all this stuff out, right? I know that the mass of the bucket is 9.2, and you could write that inside your box there. And what else do we got here? And we know that little g, which you don't always need to be told, is 9.8, right? So you need to make sure you know that meters per second squared. Okay, now which one of these accelerations, because we know that acceleration due to gravity, that's what little g is, which one of these is acting as the net acceleration for the entire system? Well, we said that this thing is accelerating upward at 3.5 meters per second, so this is going to contribute to our net force. Okay, this is going to contribute to our net force. So we first need to figure out if we want to know what tension is. I know that tension and gravity, they combine to make force net, right? So I got force tension. Is it going to be minus or plus gravity? Minus force gravitational, right? So can I figure out force gravitational? Well, remember when we do our free body diagrams, this was the first step we always take. Force gravitational means weight, and this is mass times gravity, right? Our mass in this case, boom. This is why I tell you to write the equation first, because now it's just as simple as plugging numbers straight in. 9.2 times 9.8. I don't know what that is off the top of my head. 2 times 9.8. Okay, so we get a weight of 90.16. So our weight is 90.16, and where would that go? That 90.16 newtons is going to go into force tension, net, or gravity. And that's very important because that's why we write these things down, because I could plug it into anywhere, and it would look great, but it would be wrong. Okay, so I had to make sure I got all this stuff down. So I'm going to move this up a little bit. Okay. All right, guy. All right, never mind. Okay, well, it goes into force gravitational, right? This goes into force gravitational. So we got the first part of it, right? Now, I don't know the force tension, but I suspect that I can get the force net, right? What is my other way of getting force net besides the summation of the forces? Well, my force net can come from Newton's second law, right? Newton's second law right here, Newton's second law. All right, so let's see. I got acceleration equals F net over m. Which one of these do I have? I have acceleration of the entire system, right? And I have my mass. So how do I solve for force net? Multiply by m on both sides, right? So force net equals mass times acceleration. My mass was what? And again, look, I'm just getting it from right here. This is why you want to do this. My acceleration is at 9.8. No, it's not. That is not what is accelerating the mass upward. we got to use 3.5. So you see how we have multiple accelerations this time. We have to be very careful. Okay, I'm going to get rid of some of this other stuff here. Okay, let's get rid of that, so that way it's a little bit less messy. Alrighty, here we go. My mass is 9.2, my acceleration is 3.5, and that gives us a force net of 32.2. And remember, we got to be careful. We don't just want to grab this guy and put it up here, right? That's not my force tension. That is the net force. This is why you never want to just throw numbers around on paper, because we got all kinds of forces all over the place. Okay, so my force net, and I shouldn't have erased that, but my force net was going to be force tension minus force gravitational. And now if I'm solving for this guy, how do I get rid of force gravitational? All I would have to do is add it to both sides, right? So I would add force gravitational to this guy right here, and I would get my answer. Okay. All right, so that's it. Let's move on to the next problem. All right, so let's see. Then we had number 9, because number 9 helps you with a couple of other problems. Let's look at 8. A 50.5 Newton object is in free fall. What is the magnitude of the net force which acts on the object? This is a vocabulary term. You need to know that free fall means only under the influence of force gravitational. So if it only has force gravitational, that is the net force. Force gravitational is the net force. It's acting as the net force. Okay, but number 9 kind of gets us into something different, so let's look at that. That 50 point, whatever it was on the previous page, that 50.5 that we had on the previous question now is going to encounter 18.8 newtons of air resistance. This is a slightly easier problem than what we were just doing, right? That elevator tension problem is really, really difficult. Okay, so what is going to be the net force if you have 18.8 newtons of air resistance? So here's our free body diagram. We don't need to calculate force gravitational because they already gave us the force gravitational. They gave us the weight. They gave us 50.5 newtons, and now I have an upward force of 18.8. That's nasty. All right. Okay, 18.8, and what's the function there? We're just going to subtract, right? Okay, very, very simple. All right, number 10. You're just going to have to use your judgment on that. All right, 11. Let's look at number 11. This one's a little bit different. Which is greater, an acceleration from 25 to 37 or 91 to 99 kilometers per hour if both occur in the same time? So this is a proportional analysis type of question. So what we're going to do here is we're going to do acceleration 1 versus acceleration 2. Okay, so we got to write the equation for both. V final minus V initial over change in t. And this is all for A, right? This is A1. So we're going to say versus Vf minus Vi over change in t. And keep in mind that these two changes in t are equal. So it doesn't matter what we plug down there. We could put a 1 if we want, okay? So let's go ahead and plug them in. So remember, final minus initial. Final, initial, right? It helps to label these things, otherwise you're going to mess it up. 37 minus 25. Remember, it's over the same t final. Versus 99 is my final to 91, okay? 99 minus 91 over the same change in t. Remember that these two guys are the exact same. Okay, so you can kind of use your judgment there. But that's how you do these types of problems. All right. Moving on. Let's see, number 12. Nope, you guys can do that one. That's easy. Nope, it's all vocab. All right, there we go. Let's do 15. Car traveling a straight line has a velocity at blah, blah, blah. After 5 seconds, it's now that. What is the average acceleration during this time? So as soon as you see that, remember, guess method, put the equation down. I could do this if I want. Oh, acceleration is F net over mass. But then I look and I go, did I have force? Did I see any newtons anywhere in the problem? Are there any newtons? Any newtons? No. Meters per second, seconds. That's velocity. Seconds. So this guy's no good. So I'm kind of going a little bit roundabout, but I want to show you kind of a technique you can use if you're not sure how to do these problems. So what else do I have? I have v final minus v initial over my change in time. Now let's do a checklist. Do I have v final? Okay, well, I got that one, and I have another one. Okay, after, that's final, right? That's v final. That's v initial, right? That's why you want to write these things out. So I got that, and I do have a time interval from 0 to 5 seconds. That's my change in t. Okay, so let's go ahead and do that guy. Okay, so we got 13 minus 3.52 over my change in t, 5. That's easy, easy, easy. Now remember, had I gone the opposite way, had I gone at 13 and then I slowed down to 3.52, I still want to write this equation down because look what happens. V final minus V initial over change in t, but now look what happens. If I had done the opposite, I had started at 13 meters per second and slowed down to 3.52, now it's going to be 3.52 minus 13. Minus 13. So look what's going to happen there. You can kind of think about, compare the sign. Think about what's going to happen with the sign. All right? All right, cool. Next. All right, then we got, oh, and by the way, real quick, I just want to make sure we all know how to do this. A equals F net over M. Here's how you solve for each one of these variables. So to solve for F net, we said you multiply by M on both sides. Whatever you do on one side, do the other. MA equals F net. But what if you need to solve for mass instead? Okay, well, you can do all this mumbo jumbo where you multiply by M, and you have MA equals F net. I still need to solve for mass, so I divide by A. But guess what? There was a quicker way to do that. In geometry or in just numbers and proportions in general, you have this thing called exchanging the extremes and the means. So what that basically allows us to do is check this out. If you have a guy on top of a proportion and a guy on bottom of a proportion, top and bottom, guess what? You can just swap them out as long as everything is itself over 1, yes? 100 is 100 divided by 1. So technically speaking, this is a proportion. You'd be able to cross multiply these. So you have F net equals AM, right? And so that's all we did. We just really exchanged it. If you're cross multiplying, it really doesn't matter if I put this A down here or up here, right? Because I'm still cross multiplying. So that's called exchanging the extremes and the means. But in short, you got a top and a bottom. You can swap them. Top and a bottom, top, bottom, swap them. Okay, just switch those out. So A equals F net over A. Okay, that's how you would solve for that one. Okay, just easy, easy, easy. All right, last couple. Let's see. Let's look at 15. All right. Well, we just did 15. What am I talking about? All right, let's look at, that helps you with 19. And I think we just have like one more little thing here. Let's look at 21. 21, I'm really not going to say much. Position versus time graph, we've done a whole lot of these. Moving along the x-axis here, the object's initial position is 1 meter. Now just be careful with that. Whatever displacement you end up calculating, make sure you add this back to 1 meter, okay? Because otherwise all your answers are going to be off by 1, or whatever your number is, because mine is different from yours. So let's see here. I wish that stuck to it, but it doesn't. So let's look here. Find the instantaneous velocity at 0.5 seconds, so we really don't need that at all anyways. But 0.5 seconds, we have to look at the scale. So 0 to 1, 1 to 2, so we're going by 1, so 0.5 is going to be right there. 0.5's here. Bam. So my instantaneous velocity at that point on the graph right about there. Now, what's the problem with finding the instantaneous velocity of a single point? Well, remember, velocity on this graph is the what? Velocity is change in x over change in t. My change in x is position. That's my change in y. My change in t is my change in time. Look at that. That's my change in x-axis. So I'm looking for the slope, right? So since I can't do the slope of just one point, because this is y1 minus y2 over x1 minus x2, I can find the slope through the entire segment here. Okay, so that's what you got to do. All right, cool. Bye-bye.